In this video, we continue our theme of looking at reactions that involve deprotonation of the alpha position by exploring the so-called Claisen condensation. In the Claisen condensation, what we will be doing is reacting 2 units of ester with a base to yield what's referred to as a beta keto ester. So I'm going to go ahead and write some of that out, which is that we're going to take 2 ester molecules in a Claisen reaction, or Claisen condensation as it's called. And in this reaction, those 2 ester units are going to react with a base, and this is going to be a very specific base that we'll be using here. I'm going to get into that in just a moment about what the characteristics of that base have to be, to give what's referred to as a beta keto ester product. A beta keto ester, we can decipher what the structure of that will look like by drawing out an ester functional group. So remember that an ester has a carbonyl group directly bonded to an oxygen, and that oxygen is directly bonded to an R group, where R is a carbon-containing group of some sort. So I'm going to put R equals alkyl group to remind you that that can't be a hydrogen there. And then, much like in our earlier videos where we were looking at ketones and we defined the carbon that was adjacent to the carbonyl as being the alpha position, we still do that here. And then we continue onward, and since this is called a beta keto ester, what we have to put here at the beta position is a carbonyl group of our next unit here. And I'm just going to go ahead and put R over here as well to indicate that could continue onward as a carbon chain or a ring or whatever else. So this is referred to as a beta keto ester because we have an ester group, and then beta to that is the carbonyl group of our ketone. So we are going to accomplish forming this type of product by reacting 2 ester molecules with a base. And as we do this, I'm going to go ahead and fill this in generically for starters here. The 2 ester molecules that we will work with, I'm going to go ahead and plug in here as our first ester, which I will put in like so. And we'd react 2 units of that are identical to one another. And the particular structure of the base that we use has to have an R group that matches what we have here as R prime. So the base that we use would be an anionic base, in this case NaOR prime, where that R prime is defined as the same structure that we had over here. As we go through the mechanism, we'll see why it's essential that these 2 be matched with one another. These 2 have to be the same O-alkyl group in both of these 2 cases. Otherwise, the reaction will not yield the intended product. So if we have it set up like this, then we will be able to take 2 of these types of units to ultimately yield the type of product that we see here, a beta keto ester. So let's take a closer look at this reaction with some actual reactants rather than just R groups in there, so that we can walk through the full mechanism for the reaction to see how this is all going to play out in a step-by-step manner. In this mechanism, we will use as our example the reaction of 2 units of methyl acetate. So methyl acetate is what we are going to react here. And drawing out methyl acetate, keeping in mind the nomenclature of esters, the methyl part indicates that what's bonded to the oxygen has to be a methyl group, and then acetate refers to a 2-carbon chain with our carbonyl there, making up the full structure of methyl acetate, as I have shown here. We will react this with a base where the O-alkyl group of the base corresponds to what we have here as our O-alkyl group, following that template we were just looking at. So our base here is going to be NaOCH3, sodium methoxide, because that's going to give us the oxygen anion that we need, complexed with sodium cation. We can also use here as our solvent the corresponding alcohol. So if we have sodium methoxide, NaOCH3, the solvent we want to use for this is methanol. Because what's going to happen is that the base will deprotonate the solvent, And we want to make sure that when that solvent gets deprotonated, that's going to yield this same type of structure here. So that's why we have to have these three things matching up with one another. So in this reaction mechanism, the first thing that's going to happen is very much analogous to what happened in the aldol reactions that we were looking at with aldehydes or ketones. And that is that in the first step, the base is going to deprotonate the alpha carbon to yield a resonance stabilized enolate type intermediate. So let's go ahead and show that first step occurring. I'm going to go ahead and draw out my methyl acetate. I'm going to show the carbon and hydrogens at the alpha position explicitly here, and I'm going to draw a clear bond to one of those. So this is our alpha position because it is adjacent to the carbonyl group, as we have seen in that definition of alpha all along. We have a relatively strong base because we have sodium methoxide there, which means that the oxygen is going to have a negative formal charge. Sodium would have a positive formal charge. Sodium is just a spectator. It's not doing anything in the reaction. So what will happen is that the basic oxygen is going to come in and grab a proton from the alpha position here of our ester. That's going to force the carbon-hydrogen bond to break and those electrons to come up as a lone pair on the carbon atom. I will go ahead and draw out the structure of this product of our reaction step here. So we'll still have our O-methyl group there. At the left end of the molecule, we just have CH2 now with a lone pair of electrons and positive formal charge. We would also, as a result of this step, generate methanol, HOCH3. And you'll notice how the structure of this matches the structure of the solvent methanol that we were using. So just like in our aldol reactions, where we formed an enolate intermediate that was stabilized by resonance, similarly here we can illustrate why this reaction of deprotonated the alpha position is relatively favorable is due to the fact that this product is stabilized by resonance, using a similar set of electron-pushing arrows to what we saw before when we were doing resonance with deprotonated aldehydes or ketones, super analogous to that. So we'll go ahead and draw this in. Oxygen anion up here, following our electron-pushing arrows that we just drew. Oxygen here, methyl group, filling in my lone pair electrons, and we are showing the rationale for how this product is favorable due to this resonance stabilization. Now, I will go ahead and label this first step as deprotonation at the alpha position. So it's deprotonation of alpha hydrogen. Just like in the aldol reaction, we deprotonated the alpha position in the first step. Now, coming onward into step number 2 is also going to look very much like an aldol condensation in that we are going to have the enolate carbon acting as a nucleophile and attacking the carbonyl group of the second ester moiety. So let's go ahead and show that occurring. So in this second step, I'm going to go ahead and draw out the second unit of methyl acetate. So we have our methyl acetate, and we are going to react with our enolate intermediate. Specifically, we're going to react with this structure that I am circling with the laser pointer, the resonance structure on the left, that is, because that is the one that has the carb anion that acts as a very nice nucleophile. So I have that carb anion there that I've highlighted in green. So I'm going to go ahead and draw out that structure. So we have our CH2 here at the terminal with a negative formal charge, making it nucleophilic. Carbonyl group here. Oxygen of our ester. And now I'll go ahead and draw my reaction arrow here. I'm going to go ahead and label this step as step 2 is the nucleophilic alpha carbon, specifically that carb anion, attacking the carbonyl electrophile. Let's go ahead and show that taking place. So that's going to take place as the carb anion, as a nucleophile, comes in, attacks this positively polarized carbonyl carbon. That is going to result in forcing the pi electrons up onto the oxygen, as I'm showing. and create, as a result, a new carbon-carbon bond. So just like the aldol reaction, this reaction also yields this new carbon-carbon bond that I'm showing in that bright green color right here. Let's go ahead and draw the product of this step. So drawing the product of this step, I'm going to color code it like the starting structures were to help us keep track of where everything is going and where everything has landed. So we've drawn out our structure components that were in blue here in our starting material. I've shown in blue in the product as well. Now our bond that we've just created, I'm going to show in green for emphasis and because that's the color we used for the electron pushing arrow here. Now that green bond that is our new bond that connects this carbon over to the carbonyl, I'm going to go ahead and now draw this group that was in black on the reactant side and black on the product side as well. So we have our methyl group, we have our carbon-oxygen single bond with 3 sets of lone pair electrons on that oxygen. We also have our oxygen bonded to our methoxy group there. So I have drawn now, outlined in yellow, that was our ester that was attacked, is going to become this here. That was the carbon that I've highlighted in yellow on the product side, is what it started off as the carbonyl of the ester group. The ester group, carbonyl, pi bond came up onto the oxygen to give an oxygen anion. The methoxy group is still bonded there, and the methyl group that was over here on the far left side of the screen with the laser pointer is this methyl group right here. And again, our new carbon-carbon bond, that's the magic, is in green. So we have that in place. Now, at this point, we are going to diverge a bit from the aldol reaction because in the ester, unlike in the aldehyde or ketone, we have a relatively good leaving group in this methoxy group that we have in our product here. We saw in the last chapter nucleophilic acyl substitution reactions that we could easily break this carbon-oxygen bond as a carbonyl group reforms because this carbon heteroatom bond is relatively weak. And so in the third step of this mechanism, in contrast to when we were reacting with aldehydes and ketones and we didn't have any heteroatoms to break away because we had carbon-carbon or carbon-hydrogen bonds in aldehydes or ketones, here what we're going to do in step number 3 is that the carbonyl reforms as the leaving group leaves. And the leaving group there is the O-alkyl group. So now I will go ahead and show us this by redrawing our product of the last reaction here as the reactant in this subsequent step. Drawing this out, we have our methoxy group, methyl group, oxygen anion, just copying over what we already had up there. Green line designated our covalent bond that we had made in that previous step. Blue bonds here for the other what originated as the other ester group. And now, to show this next step occurring, we take the lone pair of electrons from the oxygen, we bring those down to make a carbonyl group as the leaving group leaves. And this leaving group is able to leave because we're not breaking any carbon-carbon or carbon-hydrogen bonds here. We're breaking a carbon-oxygen bond, which is relatively weak. And under these basic conditions, we can break that away to give an O-methyl group as an anion, a methoxy group, in other words. Our other product of this step is going to be that beta-keto ester, that functional group that we were previously discussing as the general type of functional group that results from these reactions. So drawing out my final product here, we have what we see in this. So we have alpha position here, and then beta is the keto position. This is why we call this a beta keto ester, because relative to the ester, there's a ketone group that is beta to there. Now, you might be looking at this structure, and you might say to yourself, it looks like in the final product that we've created here, we still have an alpha position that would be relatively acidic. In fact, this alpha position would be even more acidic than the alpha position of our starting methyl acetate molecule, because in our product here, this alpha position is flanked by 2 carbonyl groups. And so if you deprotonated this alpha position, there would be multiple additional resonance structures that could share the negative charge over each of these two oxygen atoms, therefore making the product of deprotonating this extra stable. And so what happens here is, in this particular reaction, if we leave this in base over a prolonged time, what will happen is that the alpha carbon will become deprotonated. And so, generally in these reactions, to prevent that from happening, the reaction mixture is neutralized at the end to ensure that that alpha position is protonated before it has a chance to react further. So I'm going to add that little addendum here at the end that this alpha proton is acidic, and hence at the end of the reaction, what you would need to do is add acid to neutralize, because otherwise, if you left it sitting in base for too long, what's going to happen is that this alpha position will become deprotonated, and then once it's deprotonated, that could act as a nucleophile and attack another unit of methyl acetate. So it's important that this reaction be properly timed so that once this product has been formed, which you could monitor by using some sort of chromatography technique like thin layer chromatography to monitor the formation of this, once it is formed, you would need to neutralize the reaction before the reaction continued further to give additional products that corresponded to further removing another proton and reacting this with another unit of ester, and so on and so forth, because this is going to be subject and prone to having a proton removed there. So we will do one additional example where we're going to just be asked to provide the final major organic product of the following reaction. In this reaction, I'm going to do a mixed Claisen condensation where I use two different reactants here. And we're going to go about predicting the product of the reaction. And I'm going to use as my base here, since both of these have O-ethyl groups on them, we need to match that with the structure of the base. So we're going to use sodium ethoxide here, and then our solvent matching that would be ethanol. So matching the structural components that I've highlighted in blue. So in this reaction, we can think about walking through what's going to happen here. Of our two starting structures, we know that when we treat with base, we're going to deprotonate at the alpha position. As we look at these, only one of the two starting materials has alpha protons available. That's this ester molecule on the right here. The one on the left has a hydrogen atom there. There are no alpha carbons, so there are no alpha hydrogens. Therefore, the position where we're going to remove a proton is right here. And so I'm going to show that happening to get us through this reaction, predicting the final product that would be the outcome of this. So we start here with CH3, so I'm going to show it as CH2H, showing one of those hydrogens specifically. Our ethoxide anion is going to act as the base, so it will come in. Lone pair electrons come over, attack the proton here. That forces the carbon-hydrogen bond to break, and that is going to give us, as a result of this step, H2C with a lone pair of electrons there. We come over to the carbonyl group right here. We have our O-ethyl group there, and our other product of this reaction will be ethanol, whose structure, as no coincidence, matches that of the solvent. So now that we have done this first step of deprotonation of the alpha hydrogen, the next step is that in step 2, the enolate carbon nucleophile is going to attack the electrophilic carbonyl. And as we look at the reactants and we think about what particular carbonyl the nucleophile is going to target, is it going to target the carbonyl group of our ethyl acetate on the right, or is it going to target the carbonyl group of our ethyl formate on the left. And we have to think about which of these two carbonyls is more electrophilic. That's the one that's going to be more strongly targeted. The more electrophilic one is going to be the one on the left. And the reason the one on the left is more electrophilic is because the difference between the two structures is the presence of a hydrogen here versus a methyl group. Methyl is electron donating, and so that's going to make this carbon less positively polarized. Hydrogen is electron withdrawing, so it's going to make the carbon right here more positively polarized and hence more electrophilic. And so therefore, the correct carbonyl group for the enolate to attack is going to be the electrophilic carbon of ethyl formate. So we'll have nucleophilic carbon of the enolate come over, forms a covalent bond to the carbonyl of our methyl formate. As that is occurring, the pi electrons have to go up onto the oxygen to avoid going over the octet rule, and we have created, as a result of this, a new carbon-carbon bond. So I'm going to go ahead and draw what we will have created out of this. I'm going to highlight for us in blue what originated from the structure that I'm highlighting in blue in the reactants. I'm highlighting in blue down here in the product as well. So this CH2 group that I have highlighted in blue and I'm showing with a laser pointer in the reactant, that's what formed a bond to the carbonyl group of our other reactant. So therefore, here on the product, down in the lower right-hand corner, this is the position where I need to make a new carbon-carbon bond, and that's exactly what I'm going to do. So I'm just going to make a carbon-carbon bond to here. That represents the new carbon-carbon bond that we're creating with our electron pushing arrow coming through here. So it's what was our electron pushing arrow. Now we come to the carbon that was the carbonyl on our reactant right here. That's going to be now a carbon-oxygen single bond, so I'm going to draw that in as a carbon-oxygen single bond, 3 sets of lone pair electrons, negative formal charge. There's also going to be a hydrogen there, and there's also going to be a O-ethyl group there, so we'll fill that in as well. And now, with that, we are down to the home stretch because in order to finish this reaction off, what's going to happen is that the carbonyl reforms as the leaving group leaves. So let's show the carbonyl reforming. Lone pair electrons come down to remake the carbonyl. Can't go over the octet rule, and so we break the weakest bond, which is going to be the bond to the oxygen. That is our leaving group. So our product of this is going to be the ethoxy group, or the ethoxide anion to be specific there. And our other product of this reaction, the organic product of interest, is going to have our hydrogen adjacent to a carbonyl group, going on down the chain here, like so. And this would qualify as our beta keto ester, or beta aldehyde in this case technically, but either or, because we have our ester group and then alpha position, and then next door to that is our carbonyl group of an aldehyde or ketone. And so with that, we can circle this as the major expected organic product of this particular reaction. So with that, we'll conclude our Claisen condensation reaction. In the next video, what we're going to look at is the scenario of an intramolecular Claisen reaction, where we have 2 ester groups within the same molecule to react with one another and create a ring in the product. We refer to that particular reaction by the special name Claisen condensation, which is where we are doing an intramolecular Claisen reaction. So that video will give us some more exposure to this concept of reacting esters by deprotonating the alpha position and then using that deprotonated alpha position as a nucleophile to attack a carbonyl group of a second reacting ester.